some bioswales and rain gardens in Lancaster that had some trouble with salinity, and the landscape architect in charge thought that it might be due to road salt. And so we decided to start looking into that. And so before we can talk about the plants, we have to talk about the road salt itself. So in the United States and practically any country that has winter season and goes below zero, sodium chloride is used worldwide for de-icing purposes. And it's used because it's cheap, it's readily available in massive quantities, and it's used, it's found all over the world in mines or other locations. Sorry about this, a little nervous. It's odd talking to a screen. So in many places in the United States, especially areas like rural New England, the last 30 years have shown an increase in traffic, especially due to the increase in popularity of winter recreation. Sports like cross-country skiing and downhill skiing have really increased the people driving from New York or Boston up to New Hampshire, Maine, the Poconos in Pennsylvania. And this incentivizes the local departments of transportation to more heavily salt the roads because it's important to keep the tourists safe. The problem with road salt is there's many well-documented downsides to it. There's corrosion of both vehicles and road surfaces. Anyone that has lived any amount of time in Pennsylvania knows that a car is highly unlikely to last past 200, if you're lucky, 250,000. If anyone has a car that has lasted past that 250,000 miles, I'd love to know what it was. But road salt also contaminates groundwater and surface water, and this has been increasing in recent years. Sodium chloride specifically can alter the soil structure. And last but not least, and what I'm like to focus on, all of these can combine to cause damage to roadside vegetation. So the United States EPA does not consider road salt a pollutant, and therefore there's no federal mandate for application. There's no maximum. There's no no control over how much is applied. That's not to say that states don't do this, but it's only been in recent years that states, I want to say Minnesota is one that has put caps on how much salt can be applied, just because salting is driven by risk and liability. Like I said, there's been an increase in rural traffic and winter traffic. People are getting more confident. There's more four-wheel drive cars out there. So because it's driven by risk and liability and not environmental concerns, people are more willing to salt the roads heavily and remove as much ice as possible. And now, if you went to Home Depot or Walmart or anything and buy yourself a bag or bucket of de-icing salt, there's a good chance it's distinctly different than the stuff that they are applying to the highways. Consumer de-icing salt usually contains magnesium chloride, calcium chloride, potassium chloride, other salts that I'll explain a little bit more later, but help to mellow out the effects of the sodium. Whereas the big departments of transportation like PennDOT, they only use the sodium chloride mixture. So speaking of PennDOT, they use a combination of brine spray and rock salt to de-ice roads in the winter. The brine is officially 23.3% sodium chloride and the rest tap water. That's obviously, it depends on who mixes it, but that's their goal amount. But PennDOT uses quite frankly, an obscene amount of salt. It's hard to imagine exactly how much is used. um, it's estimated that Pennsylvania alone uses 900,000 tons of salt and 9.8 million gallons of the salt brine um, each winter. And that was an estimate from 5 years ago. They say it's been steadily increasing, but these were the latest numbers I could find. So in 2016 to 2017, Center County alone applied 15,914 tons of salt and 272,000 gallons of brine. And that's over about 1,500 snow lane miles, which if there's a 2-lane road, that's 2 lane miles per every lane of, or per every mile of roadway. It's a significant amount. This does not include municipal agreement miles. So the State College Borough has their own salting agreement. And like I said before, the consumer salt is often different from the industrial stuff that's used. The townships and boroughs with these municipal miles are much more likely to use magnesium chloride or calcium chloride mixtures because they're much less harsh on masonry, even though they are distinctly more expensive than sodium chloride. Can I click? Oh, there we go. So we all know salt dissolves very, very readily in water. And so when the sodium chloride is applied to the snow, it increases the melting point and dissolves. And sodium chloride easily permeates through the roadside soil through quick and easy dissolution. The chloride ions move freely through the soil. They're not hindered by any of the soil particles. And so because of that, they tend to go directly into freshwater and groundwater systems. The EPA, so even though the EPA doesn't have standards for road salt application, there are guidelines for chloride amounts in water. And they say it's 230 milligrams per liter, which most waterways, a lot of urban waterways in the Northeast, if they aren't past that, they are steadily approaching. And there's been topics of discussion where even now the rural waterways are getting increased in chloride content. I think I read somewhere that the Schuylkill River in Pennsylvania will be no longer habitable to aquatic animals in a couple years if continued at our current salt pace. And so the high salt content not only is just, it can stop aquatic life, plants and animals from regulating sodium levels in their own body, but it also reduces water oxygen level, which is very bad for native fish populations and other animals. Unlike the chloride, the sodium ions interact readily with the soil. So sodium affects cation exchange capacity, and cation exchange capacity is important. It's the total ability of a soil to hold exchangeable cations, and that means essential nutrients, and it also provides a buffer against soil acidification. So this cation exchange capacity, CEC, is mostly associated with soils that have high levels of organic matter and clay content. Both of those are good indicators that you have a healthy high CEC. However, in areas with high road salt application, negative correlations occur between sodium CEC and calcium CEC. And that negative correlation indicates that sodium preferentially displaces calcium from exchange sites on soil particles. And that creates an increase in calcium further down the line in the groundwater It does the same with other positive ions. Potassium and magnesium are also shown to be in increased levels in groundwater when there's high sodium application to the soil. And that can be a good thing, especially for potassium-starved plants. The increased the increased competition from the sodium ions frees up potassium ions for plants to absorb, but it's negligible compared to some of the damage that can be done by replacing all of your cations with sodium. Um, and so that measurement is called SAR, sodium absorption ratio. It's it's more common out west in the United States. Um, I hadn't heard of this until Rob brought it up, and I'm guessing it's uh, quite common in New Mexico. Um, Officially, it's the ratio of um, charge contributed to a soil by sodium to that contributed by calcium and magnesium. And SAR is important because even with a sodic soil, a slight increase in water salinity can um, cause severe plant damage because the plant is more susceptible to the sodium that is present in the system. Um, so officially the EPA and other governing bodies call 13 the cutoff for a sodic soil. However, you can find problems at lower numbers. It's 13 isn't a magic number where you're going to have problems, or you won't have problems up until that. So soils with high SAR values can affect plant growth majorly because there's well, if your plant is sensitive to sodium, then that's bad because there's a lot of it in the soil. But the soil structure degrades. The soil particles spread out and the soil gets crusty. Water infiltration is affected, and otherwise the soil is often becomes alkaline. And which can lead to nutrient deficiencies in the plants. So it's a very important metric that we don't tend to run into too often in on the East Coast, just because there's enough hard water rain, and the calcium and magnesium in the rain balances out any sodium. That, and we don't tend to irrigate with groundwater like they do in deserts and other arid places. So that's where bioswales come in. This is focusing on plants now. So bioswales are stormwater catchment areas that are built to handle the influxes of potentially polluted water, generally from rainstorms. These biofilter systems, they remediate the stormwater both with the plants and the soil. Nutrient removal is key. That's I guess the big purpose. You see them built along roadways, along parking lots, along parkways. There's to keep nutrient levels that are being washed off and pollutants that are being washed off these surfaces from leaching too much into the groundwater. So the majority of the removal is facilitated by the media, but vegetation is crucial to the dissolved nitrogen and phosphorus uptake. And there's been some more studies on heavy metal uptake and whatnot. But what hasn't been discussed so much, oftentimes when they test plants for bioswale use, they're testing them in a vacuum, and soil salinity isn't really taken into account, which is why species selection is critical. And one of the things that we had discussed about these bioswales in Lancaster that were having trouble with their plants dying was, did they even consider that Lancaster might be using road salt? I'm not sure. I haven't talked to the landscape architect. So the plants must be able to survive in sandy soils and high water levels. They must be happy in drought conditions and flood conditions, just by nature of being in a very well drained bowl. Traditionally, pollutant uptakeability has been the driving force behind selection, but if you add in salinity, then that mixes things up. And so we wanted to find plants that would handle the increased salinity well, um, especially because especially from residual salinity, especially in the spring. Um, there's still a lot floating around out there in the soil. So that brings me along to my greenhouse experiment, which consisted of 7 species of bioswale-ready plants of varying notoriety with their salinity ability. There were 3 monocots, three dicots and 4 monocots, excuse me. The 3 dicots were an aster, pycnanthemum, and monarda. There were 2 species of carex and switchgrass and a plant called schizaccharum, which I believe it's called little blue bottle, something like that. The plants were planted in pots that were 4-inch in diameter and 12 inches high. The pots were filled with a sandy clay soil mixture, which was 60% sand and 40% field soil. We sourced that from a landscaping supply company in Bellefonte. 60% and 60-40 is a fairly typical mixture for bioswales. You could go up to 75 depending on the clay content of your soil. It really depends on how quickly you need it to drain. You don't want it to drain too quickly, otherwise your plants will die, but you don't want it to become a mud pit either. Did I skip? I did skip a slide. I'm sorry about that. I think I missed this one. I thought I was missing something. There was a Swedish study, I'll rewind a little bit. There was a Swedish study that reported 75 to 90% of de-icing salt enters the roadside environment through runoff or splashing. Most of that is deposited within 10 meters of the road. And in rural areas, the drop-off is steep. It's high levels of salt very close to the road, but once you hit 10 meters out, you're unlikely to find elevated sodium levels. However, in urban areas where there's a lot more happening, there's a lot more traffic, things are splashing around and moving, the sodium levels remain high and don't really decrease as you move further from the road. And so this means that especially in urban areas, we have to be careful of the salt content that is running into our stormwater systems. Sorry about that. We'll go back to the greenhouse experiment. So according to PennDOT's very high salt application rates, they stated that they would use a minimum of 100 pounds per lane mile. So I calculated with a 5% catchment area and based on these Center County salt application rates, my 4-inch diameter pot would receive 261 grams of sodium chloride over the course of your average Center County winter. If you reduce it to a per application point, then it comes out to 1.25 grams of salt per pot per application. And so I decided to use that as my baseline. That was the standard. And then I had a control treatment of zero salt. I had and then three treatments, 50% of 1.25, 100% of 1.25 grams, and 150%. The salt was applied 3 days a week, Wednesday, Friday, and Sunday between irrigation timings. And I had the irrigation system set up to go off intermittently. And so it was set to give off 42 ounces per pot daily, but the timing wasn't consistent. I wanted it to simulate rainfall instead of one big deluge, which honestly would have caused the pots to overflow. So it was a little bit on, a little bit off, and that was spread out over 4 hours. And the salt was applied in between that time, usually towards the end, right around 9:10. I wanted it to be able to soak into the soil, but not run out completely before the day was over. So like I said, my salt amounts, there's my officials. Plants were assigned a number based on species and treatment. Numbers 1 through 20 were asters. Numbers 1 through 5 received were the control plants for the asters species, um, and so on and so forth up to number 140. I put those numbers into a random number generator and um, used a grid to align them in the greenhouse. So it was a pretty simple randomization process. Um, the salt was I told you the salt amounts. Salt was administered in a saline solution. Um, I didn't want to put down the crystallized salt. I didn't think that would um, dissolve consistently, and so I actually found a um, meat flavor injector at Walmart, and that worked surprisingly well. It was like a big syringe, and I made sure it was calibrated properly, and it worked great. So I recommend that if you have to apply salt to something, including meat. The experiment ran for 7 weeks. It was originally going to run for 6, but then it would have had my harvest on Christmas, and I wanted to go home and eat food instead. So 7 weeks it was, which was nice because it gave me 8 solid data points. Speaking of data, measurements were taken weekly every Monday. I measured a bunch of different things. I wanted to collect more data maybe than I needed or could use. And so I collected SPAD levels for chlorophyll content, the electrical conductance of the effluent water. I used a Munsell color chart to compare it to sample leaves each week, which more on that one later. And then um, one of the other things I did was I created a visual score system that I wanted to use to create a composite score. So there were 3 categories: burn, color, and wilt, and plants were assigned a score based on percentage of area affected. So a 5 was a perfect plant. There's uh, no burn on it at all. That would be given a 5 in the burn category. However, if the color was off, then depending on the percentage is listed there, 1 through 5, 5 through 24, that score would be given. And then the scores combined and averaged out to create um, a composite. And I realize it's not a linear scale. I decided I was debating heavily going back and forth between a linear scale with um, no damage, 1 through 25, 25 through 50. But I decided in the end that if we are to look at the plants purely from an aesthetic standpoint, as a passerby, if you see a plant that is 50% wilted or 50% burnt or 50% discolored, that is not an aesthetically pleasing plant. So at that point, you may as well have scored it very low. And 50% to 75%, it doesn't matter so much um, to the consumer, at least in my mind. I'm sure there's others that might disagree. It could have made a messy composite. Either way, after 7 weeks, I harvested root and shoot biomass and dried both of those. Um, the roots were a trip. That was a long couple days in the greenhouse, hosing down those. I also took soil samples from each pot, and I've sent those off to the Ag Analytical Lab. We're waiting to get back some results, and so hopefully I'll be able to calculate SAR value from that. Um, So these pictures are about 3 or 4 weeks into the experiment. Um, I can't remember the exact date that I took them. I should look it up, but I thought these illustrated. This is the Monarda. I thought these illustrated the level of salt damage pretty well. Monarda was very susceptible to even the slight level of salt damage, and 3 or 4 weeks into the experiment was about the time where I really saw the effects take place. Um, in the case of this Monarda, you can see, I guess the order is kind of odd, but this plant here is the control. This one here received 50% of um, the lowest level of salt. This received the middle level, and this received the middle level, and this received the highest. Um, Monarda was one of the plants that had very few survivors all the way to the end, especially in the high levels of salt application. Um, Overall, the dicots did much worse, um, which was as expected. Um, here's another 3 weeks in example. The pycnanthemum, over here on the left, this is the control. It looks pretty good. There's a little bit of discoloration, but the pots were very small, and I think that contributed to some of the misgrowth. The other master's student in Dr. Hoffman's lab, Jacob, he was growing plants in 5-gallon buckets, and I think they had a lot more room to spread out their roots, and um, they ended up looking a whole lot healthier, and even mine that weren't being bombarded by salt, just yeah, I don't think they could compare to something that was grown in a much bigger pot. So that was something to keep in mind for the future. Um, but this one here, the one on the right, received the moderate amount of um, salt, and you can see already the burnt tips. The Monarda or the Pycnanthemum slowly turned purple most of the time. I believe that's a sign of oxidation, but I couldn't remember off the top of my head. I'm sure someone could correct me. Um, Here's a picture of the aster. This picture is taken at the end of the experiment, um, and you can see the picture on the left has the control aster, which is still not looking so great, but it was towards the end of its lifespan. It had already flowered, and so I think it, I think I could attribute most of the discoloration to general senescence. Um, that and the small pot didn't help. However, the one on the right was given the highest level of salt, and that did not fare. I think that one died maybe 3 or 4 weeks in. Um, I remember that one being particularly stressed by the salt. On the other hand, the monocots did um, fared much better. Uh, on the left, here's a carex that was given no salt, and a carex that was given on the right is a carex that was given the highest level of salt. All things considered, it doesn't look that different. I'd say both of them looked distinctly worse than the plants that were grown in larger pots. Um, but at the end of these 7 weeks, there was not a whole lot of difference. There was a noticeable difference though, and that's reflected a little bit in the visual scores. The last two species I had a little bit of difficulty with, especially towards the end, giving out the visual scores. The color, I felt that it was neither of these plants. On the left is switchgrass, panicum, and on the right is the uh, schizaccharum. And neither of these plants were super colorful to begin with. And so it was hard to tell what was senescing, what was burning, what was dying from salt stress, and what just looked kind of gray from the start. So both of these, I think later on I'd like to try removing the color score from their composite to see if that changes and see how that changes, um, because I'm sure it would create quite the difference in the visual score composite. Um, I've compiled some graphs of some of the data. I'm still working through a lot of the some of the more complicated data collection, but I think this preliminary data shows some pretty interesting stuff. Um, the shoot biomass, so the plants were fully established when they went into the under the salt treatment, and I wonder how much that affected this. Um, Obviously, I think um, giving plants salt as they're trying to establish is not representative of a um, plant that has been there many years. However, I think it's fascinating to see what's happened when the plants have already been established. Um, and so it was interesting to me. Some of these standard error bars show some significant differences, but not that many. Um, Here and there. For example, the Monarda, the control group fared distinctly better than anything that was given salt, though the level of salt didn't matter so much. Um, the grasses had a higher biomass overall, but um, I'm not sure that they're comparable just because of the way that they grow. I wouldn't say that I could compare the species to species mass wise like this. Similar story with root biomass, except this had a little bit more outliers. I would attribute that to the difficulty of washing roots. There's always going to be things stuck in them. Um, Apparently, there was likely a lot of stuff stuck in the Carex camosa root system because that's a very heavy root system for a very normal sized plant. Um, that being said, it was nice to see some trends here and there, even if they weren't statistically significant all the time. I did like seeing that the aster slowly decreased in root biomass. It did make me wonder then if the roots were dying as a result of salt. Sometimes I wonder. I thought maybe we would see an increase in root biomass as the plants became stressed, but doesn't really seem to be the case anywhere here. Um, this next one's a graph of root to shoot ratio, um, which I thought painted another similar picture, um, showing some trends here and there, but I'd like to dive a little bit more into some further relationships before I try to make any conclusions from something like this. Um, Especially because this pycnanthemum all over the place. Some of these confused me a little bit, but I suppose it can't all be perfect. The SPAD readings showed me less than I had hoped. SPAD's just a measure of greenness, and therefore chlorophyll content in theory, but I found that even some of the brown leaves, when um, if I used the SPAD meter on them, they would give off um, a decent reading. And so some of these plants, even though they looked very dead, their SPAD readings were still normal. I didn't add standard error bars to this because it was confusing and they all overlapped anyway. But these are the dicot SPAD readings, and here's the monocots. I think the panicum was the only one that showed a statistically significant difference in week 6 and 7 with the SPAD reading, um, which that to me is interesting because um, and that's something solid. I like that. Um, a similar story with the EC, the effluent EC readings. It's much of what I expected. The um, the salt level in the soil seemed to reach um, a somewhat of an equilibrium, and as I was adding it, however much was leaching out, stayed relatively constant from week 2 onwards. And same thing happened with the uh, the monocots. I am interested that all of these show, or most of these show dips in weeks 4 and 5. That might be on me, a calibration error, but I'd like to look more into it and see if I can find any correlation with anything else. Um, the visual score actually, I think, was one of the most conclusive parts of my preliminary data. Um, there shows a lot of there's a lot of distinct trends here, which is nice because I had hoped this is only the final week's visual composite score. Um, so both the aster and the pycnanthemum, um, none of the plants that were given the highest level of salt survived to the end of the experiment. All they were all dead. The Monarda, similarly, I think there was a little bit of life there, but it looks like it's about 0.25, so maybe one plant survived. Whereas the others did a heck of a lot better. And like I said earlier, I think the color aspect dragged down the panicum and the schizaccharum as they were going through, I think, what was a normal senescence. They lost a lot of their color, and so I'd be interested to remove the color from the score equation and see how that affects the two of those specifically. Though it is nice to see a trend from both of them. So in the next couple weeks, I have a lot on my plate on the horizon. I have some big plans with the rest of my data. I have root samples that I have stored in 50% ethanol. They're in little baggies. So I'd like to do a specific root length using WinRhizo. I plan to take those root samples and scan them to measure the sample root weight length, and then dry them and weigh them. And then hopefully I'll be able to compare the sample root mass to the total root biomass and maybe get an estimate for total length. I know that's it. It wouldn't be perfect because the thicknesses of the roots are variable, but I'm hoping there's something there. I'm waiting to hear back from the Ag Analytical Lab about the soil SAR and other nutrient levels. I'd like to see how those changed over time, and I have original soil samples too that I sent in as a control. So I'm curious to see how the plants affected it versus everything else. I'd like to look at send in shoot biomass samples into the Ag Analytical Lab to see their nutrient and salinity levels, and maybe take some pictures with the XRF machine to see if there's sodium even in the leaves. I think we could see maybe a distinct difference between the controls and the highest levels, for example. I'd like to look at the root samples under the laser. I think there might be some correlation between number and size of xylem to the salt treatment. Plus, I think for most of these plants, or at least a few of them, I don't think anyone has ever lasered their roots before, and so it'd be nice to see a picture and at least have that for future reference. I'm on the track to do some deeper diving into the statistics. I'd like to compare a lot of these variables that I showed you earlier and um, pit them against each other to see how they have been interacting, if they are interacting at all, and if it's relevant or not. Um, and I'd like to revisit the final visual score, um, again, based on the color of the panicum and the schizaccharum. Um, I, it's been on my mind for the last couple months. And so with that, I'd like to thank everyone that's helped me, my advisor, Dr. Hoffman, Jacob Matlin. He was a huge help mixing all the soil and filling the pots with me, and everyone else who's helped me along the way, Dr. Burgage, Dr. Selmer, Dr. Lasky, everyone else who's listened to all my questions, all my ideas, given me guidance and given me tools to collect all this data. So thank you. And if there's any questions, I'll try my best to answer them.
We have some time for questions, if there are any questions for Tim.
I have a question for you, Tim.
Mm-hmm.
So you said in your methods that you were applying a saline solution based on wintertime measurements, correct?
Yeah.
Had anybody taken soil samples from that region because you're testing based on what's being experienced in a specific region, correct? It was something along the side of the road in Lancaster.
We had plans to do that, but then with the COVID last spring, the city of Lancaster didn't want outsiders coming into their town. So the plan kind of changed there. I think it would be really cool to see how long the salt stays in those bioswales, and there's a few of them there that are ripe for investigation. I think if we set up and took soil cores throughout the winter, spring, and summer, I'd be very interested to see how long the salt truly stays there, because I do believe, at least in Pennsylvania, most of the sodium washes out. It slowly builds up year after year. And so maybe after 15, 20 years, there might be an accumulation that's noteworthy, but it's hard to tell after one summer.
That was actually kind of, yeah, that was kind of my question, was what kind of residual concentrations might remain during the summer months, and how realistic are those concentrations that were used to what the plants will actually be experiencing out in the field, if you're looking to kind of transfer this to a real world scenario?
Well, obviously no one is salting their plants during the summer when there's no snow and while the plants are growing. There is the other application is seaside towns. The closer you are to the coast, the more salinity there is, even in the rain, your irrigation water. So salinity isn't, I guess, tied down to the road salt. And there have been some studies into how much residual salt there is. And I've seen some very differing opinions. Some people say a negligible amount. Some studies say that it accumulates enough that you'll see a difference in 5 years and your plants might be dying by then.
Thank you.
I'm sorry. Yeah. Thanks. Yeah. I hope that answered your question.
Yes, thank you.
So Tim, if you don't mind me interjecting something,
Mm-hmm.
This is Dr. Hoffman. So Emily, concerning your question, so Lancaster has reopened up and we are doing soil cores now, and we'll continue to do them through the summer so that we can, develop some understanding of how long or where the salt is moving in the soil. which is part of what we want to look at. There's a lot of research that's been done both out west and in Minnesota and Wisconsin concerning highway salts, road salts, and they're finding that they are seeing an increase in salinity of groundwater and also of receiving waters. Like, so those are, Wisconsin and Minnesota have a lot of lakes, and it's becoming a real issue for them. So it's definitely something where it's not going away. The soil or the salt is retained in the soil, but also being transferred to local waters. So there's a lot to look at in this issue, I think.
Yeah, if you do a dive into Google Scholar about it, a lot of the research is on fisheries and wildlife and streams. But it is interesting to see how it goes into the man-made structures like bioswales and constructed wetlands.
Yeah, I find it fascinating. I actually did undergrad research on summertime salinity fluctuations in freshwater streams. So
Okay.
I am very fascinated by what you're doing. I think it's really interesting, and I look forward to seeing what else you produce with this.
Thanks.
Any other questions for Tim?
Yeah, I had another question. Hi, Tim.
Hi, Lisa.
I was just wondering, because I don't really know anything about bioswales, like, is the age of your plants during your experiment also like the same age of like when they install bioswales, they also plant the same plants like at the same stage and they begin dealing with salt stress like right away, or are the plants a little older, and like how often do the plants in bioswales get replaced, because they, I assume, can't like survive forever under enduring salt stress, right?
I think there are some bioswales out there that are fairly well established, and especially if you have enough salt tolerant crops that or plants, then they'll survive for quite some time, if not indefinitely. I think a lot of what can come back to bite the builders is if you try and put the plugs in too early. And I'm not exactly sure the time of year that most bioswales are constructed. I'd assume it's in the spring and summer.
Okay,
but-
yeah, I think that would be a cool concept to play around with, because like if you can't
Mhm.
change the amount of salt entering the system, you could like change the timing of when you like install the bioswale or replace the plants or something.
That's true. I think it's important to have the plants as established as possible before they hit any major stressors, including winter and salt.
Mm-hmm.
And so, it, like any other plant, the more established they are, the hardier they'll be.
Okay,
And-
cool. Thank you.
I think that I'm not sure if that covered it, but
I know you kind of touched on this a little bit when you were talking about your methods in the very beginning, but what kind of consideration is given to, obviously you're hoping that these plants come back year after year to kind of continue the remediation within the soil. What kind of consideration is given to plants that are coming out of dormancy or senescence, and how that, because that's going to be when the salt levels are pretty high in the water or the soil, but that's also going to be when the energy used by those plants is pretty high.
yeah. We actually have a plan for a future experiment. Actually, I have a bunch of plants sitting outside the greenhouse in dormancy right now. Unfortunately, we don't have that many species. I think we only have one species that has enough replications to do an experiment on. But I think in the future, that's something I would be very interested in. In my mind, that's a very logical next step, if not my favorite next step, I guess you could say, to see the out of dormancy with all of the salt. It's just difficult because it's a once a year kind of spring thing, unless you have a very large freezer.
Thank you.
Any other questions? All right, let's thank Tim for seminar today. So thank you, Tim.
Thank you.
And, we'll see everybody next week.
Actually, I have a quick question for anyone still on. If anyone has used a Munsell chart to and consistently kept all of the